Problem 1.73. In this problem, two flat plates are oriented parallel above a fixed plate as shown in the picture below. The top plate is located at a distance b above from the plate and is pulled along at a velocity v. The other thin plate is located at a distance c times b, where c is a value from 0 to 1 above the fixed plate. This plate moves at a speed of v1, which is determined by the viscous shear forces imposed on the fluids both on the top and on the bottom. The fluid on the top is twice as viscous than the one at the bottom. Our task is to plot the ratio between the velocities v1 and v as a function of c, once again, when c goes from 0 to 1. For us to solve this problem, we're going to assume a couple of things. One, it's going to be that the system is under steady state conditions. Two, that the two fluids are Newtonian. And the other assumption is that we're going to have that the velocity in both fluids behaves linearly. Okay? So also note that both of the velocities are going to be constant. And one thing that we could point out is that the shear stress that takes place at the top of the middle plate is exactly the shear that takes place at the bottom. That is so that we could have continuity. Okay, so for references, we're gonna refer as the fluid in the top as T, the one at the bottom with V. Okay, so we'll start with the information of how we relate shear stress with viscosity. And this is the rate of shear strain. Okay, so this is the default information that we're going to have. So we're gonna start with the bottom. Okay, for the bottom, notice that we go from a velocity of equal to 0 to a velocity of v1 and a distance of cv. We do a little bit of algebra using linear relationships. We find that the velocity at the bottom is going to be the function of y is going to be v1 times y divided by the distance cv. Once again, if we substitute y equal to 0 over here, the velocity will give us 0. If the velocity is a cv, the velocity will be v1. Now, notice that we're going to replace this into this equation, so the next thing that we need to take is the derivative of this velocity with respect to y. So, du at the bottom with respect to y. Notice this is a linear relationship, so we only are left with v1 c times b. Okay, and then that substitutes that the shear stress at the bottom is simply the mu at the bottom times this rate of shear strain, so v1 c times b. So this is the shear strain at the bottom that describes it at the bottom. So let's do the same procedure at the top. So the first thing, we're going to describe the velocity at the top as a function of y. So notice that for this case, we have two velocities, so it goes from v1 to b. So it goes v minus v1, once again y. And the distance, the difference between the two values, which is b minus cv. Okay. So once again, it's a linear relationship. If you replace y to be equal to b, this will substitute and become v. And once again, if you do cv, it will simplify to v1. So please make sure that you do that little process. du dy. So we're taking the derivative with respect to y. Once again, it's linear, so it's simply left with the constants. Okay, and we substitute into the equation over here. So tau at the top, and it was indicated that the viscosity is twice as much as the bottom, so it's 2 mu v minus v1, and this is divided by v minus cv. Okay, so this gives you the relationship between both of the different shear stresses, both at the top and at the bottom. So the only thing that we know is that at position, so at the position cv, the value of tau at the bottom and tau at the top are going to be the same. That's the only thing that we know. And once again, it's so that you have continuity. You cannot have a jump between the values of the stresses between one point and the other. So at this position, we set that mu V1 CV is equal to this value okay, and then we start simplifying this equation. Okay, so let's start canceling things. Mu and mu cancels in this side, and then we are going to be able to factor things out. So notice that this one could be written as 2v minus v1, and we could factor out the value of b. This is 1 minus c, right? And this is b1 CEV, and b cancels in both sides. So now notice that we have everything as a function of c. We're going to do a little bit more of algebra, and then if you do that simplification, so please try it, we want to get the ratio between the velocity v1 and v. And once again, you do a little bit of algebra, and you should get to v1 v is equal to 2c divided plus 1 plus c. Okay, and then in order for us to plot it, we're going to choose some values for c, replace that into this function, and then do the plot. Okay, so we're going to do a little table over here. We're going to do different values of c and ratio v1 over v. Okay, so let's use some values of c that go from 0 to 1, and we're going to use for this particular case every 0.25. Okay, so we're going to start with 0, 0.25, 0.5, 0.75, and 1. In the evaluation, this ratio at 0 is equal to 0. At 0.25, it gives us 0.4. At 0.5, it gives us 0.66. At 0.75, gives us 0.85. And at 1, it gives us 1. Okay, so now we're going to plot it. So we're going to do from 0 to 1. So this is 0.5, this is 0.25, 0.75, and this is going to be the value of c. And this is your ratio, v1 over v. And we'll do exactly the same thing, 1. This is going to be 0.5. Okay, so now let's look at the numbers. So at 0, we have 0. At 1, we have 1. Okay, and then let's do 0.25. It's going to be 0.4, so it's somewhere over here. 0.5 is going to be 0.66, which is somewhere over here. And 0.77 is 75 is somewhere over here. So not necessarily the best drawing, but it gives you an idea of what the relationship is between c and the ratio of the velocities. So join the points, and this gives you the velocity ratio. However, please keep in mind, in order for us to be able to do this, the only way that we can do it is by having this assumption that tells us that in the middle plate, the shear stress at the top and at the bottom have to be the same. Once again, in order to maintain continuity.